Now see a lens maker's formula. Lens maker's formula actually connects the refractive index of the material, radius of curvature and focal length. And this formula is also useful for designing the lenses of the focal length by choosing the different materials. So let us discuss lens maker's formula for the convex lens. It is same whether it is a convex or concave, just sign convention changes according to the the surfaces. But if you are taking convex, suppose this is a double convex lens. There are two surfaces, this is x, p1 and y, and here is p2 pole for the second surface. This line which is passing through these two poles is known as the principal axis. Suppose object is somewhere here and I am taking two rays, incident rays like this, one is here passing through the pole and one is going to this. At this point a normal is drawn, that is from the center of the first surface. So, C1 is the center of the surface x p1y, and now this will be obviously angle of incidence. As this ray enter into this, the light goes here like this, it incidents on the another surface, and again we draw the normal over here, that is C2, this is C2 here, and normal from this point. After refraction, this now the refraction is taking place from denser to rarer medium at the surface xp2y. After refraction, this ray will be coming and meeting at this point, and finally image is obtained at I. But suppose this surface were absent, xp2y were suppose not present, then the image formed by xp1y will be obtained somewhere here, that is referred as I1. So, here this point is here, the C here, that is called optical center. For deriving lens maker formula, we assume lens is very thin, it means the distances between P1C and P2C are ignored. Object is always taken as a point sized object, these are the assumption I am discussing here, and aperture is small and the angle made by incident ray and refracted ray are small. So, under these assumptions we are going to derive lens maker's formula. So, see here, if we take the first surface, so for surface xp1y, refraction is taking place from rarer to denser medium. So, when the refraction is taking place from rarer to denser medium and this material has got refractive index mu2 and this one is here mu1. Already we have derived formula for the refractive index and radius of curvature object and image distances for convex surfaces here, and when the refraction is taking place from rarer to denser medium. So, we can write here mu2 minus mu1 upon r1, r1 is the radii of, or that the radius of the surface xp1y is equal to here mu1 upon minus u plus mu2 upon v1. V1 is the image distance for the surface xp1y. It means the distance between P1 and I1 is known as V1, and the distance between P1 and O is known as U, that is object distance, and R1 is radius of curvature. Now, if you take surface xp2y, so for surface xp2y, refraction is taking place from denser to rarer medium. It means the image obtained by first surface is acting as object, that is the virtual object for the second surface. So, we can write in that case mu2 minus mu1 upon minus r2, r2 is the radius of curvature for the surface xp2y and is equal to mu1 upon v minus mu2 upon v1, because object for the second surface is this one I1. So, we have written the formula for these two surfaces xp1y and xp2y. Now, you add these two. As we add these two, so see here there is a mu2 upon v1 and there is a minus mu2 upon vn, these two will get cancelled, and we will be getting here, after adding these two equations, we will be getting mu2 minus mu1 into 1 upon r1 minus 1 upon r2 is equal to here mu 1 upon V minus mu 1 upon U, adding these previous two equations. Now, we can take mu 1 common and to this side. So, we will be getting 1 upon V minus 1 upon U is equal to here mu 2 upon mu 1 minus 1 into 1 upon R1 minus 1 upon R2. And this we can write if I take U is equal to at infinity. So, V is equal to F at focal length. So, the same formula can be written now here 1 upon F is equal to mu 2 1 minus 1 into 1 upon R1 minus 1 upon R2. So, this is the relation between focal length, refractive index of material and radius of curvature. But see here this P1, P2 and C are very close to each other because the lenses are considered to be thin. So, all these distances are ignored here and everything is measured from the point C. Now, see here we have derived lens makeup formula for convex lens and this formula has come out to be this 1 upon F is equal to mu 2 1 minus 1 into 1 upon R1 minus 1 upon R2 and mu 2 1 is equal to that is mu 2 upon mu 1. Mu 1 is the refractive index of the surrounding and mu 2 is the refractive index of the material of the lens. It means focal length of the lens depends on the material of the lens as well as the refractive index of the medium in which the lens is placed and similarly depends on R1 and R2 and this formula is same for concave lens also. So, for the exam point of view you have to practice for the convex lens and concave lens also and in both the cases formula will remain same. So, let us discuss certain cases. If I have taken a convex lens like this is a double convex lens and here two surfaces, one is this and one is this. So, obviously, if R1 is this side and R2 is this side, if R1 is positive, R2 is negative. If I am writing R1 is equal to R, then R2 is equal to minus R. This is a equiconvex lens, both the surfaces have got the same radius. Now, if I put over here 1 upon F is equal to mu 2 1 minus 1 into that is 1 upon R plus 1 upon R and that can be written 1 upon F is equal to mu 2 1 minus 1 into 2 upon R. But now see here, if you are taking the lens is suppose glass, then we can write mu 2 1 is equal to because the lens is made of the glass and here is air. So, then mu 2 1 can be written 1.5. So, the formula will become 1 upon F is equal to 1.5 minus 1 into 2 upon R. So, that is here 0.5 into 2 upon R. So, that is 1 upon R. So, here it can be written F is equal to R. So, if the lens is made of here the glass whose refractive index is 1.5 and both the surfaces have got same radii, then focal length comes out to be equal to the radius of curvature. So, this is here the one case and also see here the focal length depend on the medium as I have discussed, medium of the material as well as the medium of the surrounding. So, now let us discuss different cases here. The different cases where the focal length is changing due to the change in the medium around the lens. Now, the first case, if I have taken mu 2 is equal to mu 1, obviously mu 2 equal to mu 1, so this part will be 0 and focal length will become infinite. If the focal length is infinite, then you know what happen, if it is a convex lens and the rays are falling like this and this is here the mu 2 and this is mu 1. So, these rays will be going parallel to this. There is no deviation in these rays because there is no actually the refraction is taking place, that is simply here the glass, it is acting like a glass sheet. If it is a concave and here this is mu 2 and this is mu 1, both are equal. So, also here the incident rays will be going in this way. It means the property of the lenses gets vanished here if the refractive index of the medium and the refractive index material of the lenses are equal. Now, see second case. In second case we can take mu 2 is greater than mu 1. We know it, mu2 1 is equal to mu2 upon mu 1. If mu2 is greater than mu 1, so mu2 1 is only positive, that is greater than 1. So, that is a positive value. If it has a positive value of mu2 1, it means the focal length is not going to be, the nature of the focal length is not going to be altered. Focal length, value of the focal length may change according to the values of mu2 and mu1, but its nature of the lens will not change. It means if you have taken a convex lens, it will behave as a convex. If it is a concave lens, it will behave as a concave. It means it will diverge. So, when the lens is placed in a medium whose refractive index is less than the material of the lens, then the nature of the lens will not change. Now, let us see the third case. In the third case, if you are taking mu2 is less than mu1, so mu2 is less than mu1, then m21 is less than 1, and in that case focal length will become negative. It means the nature of the lens will change. Suppose you have got a convex lens whose refractive index is mu2, and this is here the line, and in this case this is here the principal axis, and here mu2 is less than mu1, then this lens will diverge the rays. It means convex behaves as a concave lens. Similarly, concave will behave as a convex lens. So, if you are taking a concave lens like this, and here the rays are coming, this is refractive index mu2 mu1, and then after refraction the rays will get converged. So, now the diverging lens is behaving as a concave, as a convex lens. So, see here the dependence of the focal length on refractive index we have seen here, and you know the properties of the lenses can be altered by dipping them into a liquid whose refractive index is suppose less than whose refractive index is the greater than the material of the lens. So, this concept is very important here, and because it is actually explaining here the designing of the lenses by choosing the suitable material of the transparent materials.